Okay, so first of all, thank you, Gita-sensei, for inviting me. It was really an exciting 2 days, the days before, to listen to all the achievements that you got in the Moonshot project and also the demos that we had. So thank you very much. I'm very happy to have the opportunity to show my own research interest. I hope that some aspects are relevant to your own research. So I start with the definition that you gave about your cybernetic avatars. So they are not only remote avatars that use images, but it's also an augmentation of the physical cognitive capabilities. So, and in fact, in your definition, I found that they are embodied robots in the physical world. This is the main part. If they are embodied in the physical world, this is exactly what robotics is about, and this is exactly what living beings are about. So this is where we can take lessons from nature in robotics, and we know this approach very well. It is a very successful approach, not only in robotics, in fact, in many fields of engineering, in material science. And a few years ago, this paper was published saying, okay, yes, it is a successful approach. You see the increase of papers about biomimetic research, but we should be careful not only to use more species as models, but also to team up with biologists. It is very important that this bio-inspiration is very well grounded in science. That was a few years ago. I thought things are improving. As you heard, I'm editor-in-chief for biomimetics and bioinspiration, so it's a journal about this. But I found another paper, very recent, last year, and the situation is still the same. Very few biologists are collaborating, in fact, with engineers and roboticists. So I think if there are a few mistakes that we may do in engineering. So when we observe our biological model, we just tend to think that this is the optimal that we can try to understand, but we tend to forget that what we are observing is the result of evolution. Evolution is based on natural selection. The best organisms go on, but the goals are survival, reproduction, so not exactly what we want. And what we are observing is not optimal. It's the result of adaptations. So we must be careful not to copy. And we must be careful to really understand the principle. So this is the big contribution that engineering and robotics can give to science and can get from science. So this growth of science in bioinspiration, biomimetics, it's very much given by a good implementation of the principles that we learn from nature. So which brings the good science. So and help us teaming up with biologists, because so we can attract biologists if we do with this big, good implementation. So it's a very effective and fruitful loop. So what is this good implementation of principles from nature? From my personal view, there is a very first step that is observation and understanding. Since we are roboticists, we like building things, and here we can build what I call mock-ups to test the principles. So this is very important. It's very much based on trial and error, but it's a very important way to experimentally validate principles. But it's only when we can abstract the principles into a mathematical description that it becomes engineering, real engineering, no more trial and error only. And we can design our robots. So at this point, our robot will contain the principles and doesn't need to be similar in shape or appearance. What is important is that the principle is contained into our robots through the mathematical model that we built. So I'll put this process inside the good implementation, and we can actually get the interest of biologists in the different steps. So when we demonstrate the principle, when we have a model that describes it, and the bioinspired robot is just for our own applications and engineering purposes. So what are the principles that we can get from nature? Of course, there are so many, but there is a big one, in my opinion, for robotics, for roboticists, which is when we look at the motor behavior, sensory motor behavior of living beings, what we are observing are complex systems, so many actuators, many sensors, complex environments, so they are not moving inside a structured environment like industrial robots, but still their behavior is very fast, very efficient, so there must be tricks somewhere, not to simplify the system, not to simplify the environment, but to simplify sensory motor control. One of those principles is embodied intelligence. So this is a picture that may help me explain the principle in few words. If you look at the humanoid here, you see that the task is just walking, but on a terrain which is not smooth. Okay, so a typical robotics approach is to put sensors in the feet, in the legs, so that we can detect the steps, and then we can reprogram the motor commands, the movement, and we can negotiate the steps. But this is not what the dog does here in the center of the image, because the joints, the knee joint, for example, the ankle, are compliant. So they can compensate mechanically, just mechanically, to some extent. And if we can get this principle, as it was done in the small robot on the left, then everything can be very fast. So the small robot on the left is inspired to cockroaches that are very fast runners, and they can run on any terrain just because their legs adapt mechanically. They don't have a big brain. They don't do a lot of computing, but it's a lot of mechanical computing, what we call morphological computation. So that's very big and good news for robotics, because we understand that this sensory motor coordination, adaptive behavior comes from the interaction with the environment, so we can simplify our tasks in robotics. But we have to consider compliance in the body. So we have to consider the interaction with the environment, and we need a robot body that can accept such interactions, that is compliant, that can deform, and this is what brought to soft robotics. So the use of soft materials or soft compliance structure in robotics. And actually our surrounding and animal world is mostly soft. In my own research, the octopus has been an excellent model, not only for soft robotics, that's quite clear because it is only composed of soft tissues, but it is also an excellent model for embodied intelligence. I'll try to convince you with this simple movement. It's a reaching movement that the octopus does with an arm to grasp a prey, a target. So you see that it is a bending wave propagating from the, let's say, the shoulder, the base of the arm to the tip. And in water, this is the best movement possible because it minimizes the drag of water. What we observed by chance in our lab is that this a simple silicone thing, completely passive, no actuators, but similar shape and same mechanical properties, with just an acceleration at the base, have a very similar behavior, a bending way. So the idea that we got is that, okay, so it's not only the octopus controlling all the muscles that it has, but maybe the water is also helping in this bending. And actually we found that only 3 parameters are used by the brain of the animal to control this movement. So for me, this is a beautiful example because the movement is given by the body characteristics and the interaction with water, and control is simplified very much. So this is what can be very helpful in robotics. We studied the muscular strata. We found that this is key for this behavior, because what is interesting in the animal is that, okay, it is soft, but we don't want just soft robots that cannot do much, cannot generate force. The octopus is soft, but the muscular structure can generate forces because there are longitudinal transfer muscle, co-contraction, increase the stiffness very much. So sometimes the octopus arm is a sort of modifiable skeleton, very stiff, and can generate very high forces. So this is what we try to copy. Again, a very complex system. There are so many muscles, so many degrees of freedom in our robot, because it's an infinite degrees of freedom. But control can be very much simplified by the morphology, the interaction with water. And we built an arm with that. Let me go fast here, a full robot. We also found other evidences of embodied intelligence in the animal, in the way they walk and they swim. So again, it's a complex system that you are observing, because in terms of muscles and receptors, really huge number. They walk, as you see, using their arms as legs. Complex movement, but we understood the principle, and they are only using two legs, the back legs, and they use them by stiffening the proximal part, you see, and they shorten the leg, they attach it to the floor, then they stiffen it and push the body forward. And they also use the interaction with water to buoyance a little bit. So complex system, complex environment, but very simple control, because it's a cycling movement and can be done in robotics with just one motor. Same for swimming, it's a contraction. Of course, the morphology, we studied the fluid dynamics, it's quite complex, but the morphology of the mantle and the funnel where the water is ejected generate a very good propulsion. This is what we could copy. This is the mock-up. It's not a real robot, it's not a real prototype. It's for verifying the principle. And we verify that it can walk with just one motor per leg. There is no control, basically. And the same for the swimming. It's just a contraction, just one motor, very simple control. So we learned a lot about embodied intelligence, but are we ready to do the next step to make embodied intelligence become a model that we can use for designing our robots? So can we go forward with respect to the trial and error approach that we used in the first phase? So how to model embodied intelligence for robot design? Actually, it is quite a complex problem, because we have to model all the interactions of the body with the environment. So we have to model what we call internal interactions, meaning how the body deforms for the action of actuators. But and this is quite, roboticists are familiar with that. But what is less familiar is modeling the external interaction. So how the body is deformed by the interaction of the external environment, either solid, like in walking, or fluid, like in swimming, or the octopus reaching movement. So we just published this paper where we propose an approach to do that. So to see how to design embodied intelligence, first of all, let's see where embodied intelligence is in our robots. So this is just a general sensory motor scheme in robotics. Don't look too much at the boxes. This is not relevant. You can put any of your sensory motor schemes. This is just to outline where embodied intelligence is, and it is here. So it's sort of additional arrow from the environment. Usually we have something from the environment going into the sensors of our robots, and the action of the robot going back to the environment. Here we have an additional arrow that goes directly in the mechanical system, in the body. So it's like closing a very, very short control loop here between the body and the environment. So if we model that arrow only, Is that a good way to model embodied intelligence? This is our hypothesis, and actually, as I said, we also have to consider the internal interaction, and there are ways to model the deformation of soft bodies given by actuators that are internal to the body itself. These are possible approaches. One is by using continuum 3D solid mechanics, or we can use a specific approach that I'll describe in a moment for describing the deformation of the body in the shape of rods and shells, or we can use some parametrization of the soft body. As I said, in our group, we use this second approach. So we use the Coursera modeling method to model the, let's say, soft conical octopus-like robot arm with actuators inside that are simplified here to cables. We actually have a prototype with that, so we could verify the modeling experimentally. What is nice is that this approach fits the arm-like shape, but also the shell shape that is the shape of our octopus mantle used for swimming. So with the same modeling, the same equations, we could model both. The mantle is important for this kind of swimming movement. For the external interactions, we can broadly see three main classes, both for fluid and solids, as we see in a moment. So again, we can consider continuum mechanics, in this case, continuum fluid mechanics, or we can consider lumped parameters. Of course, today there are also data-driven methods that are successfully used in fluid dynamics, so let's consider this class as well. In our group, we could couple the two models. So the internal interaction model of the deformation of the shell due to actuators and the fluid dynamic model of the swimming movement. And you see here the comparison of the model behavior with the prototype. So this movement is, again, very simple to control. And we are happy in robotics when control is simple. But the fluid dynamics involved is quite complex. And obtaining the propulsion is possible only when you obtain ring vortexes. And all this mechanism is quite complex, and it is given by the morphology and mechanical properties. But then we have just one motor and zero control problems, basically. With solids, the interactions are modeled in a similar way, either with continuum mechanics or with parameters, and again, we can even test data-driven methods. This is relevant in robotics because walking, locomotion, is based on interaction with solid environment, terrain. So there are models for locomotion in robotics. So we modified one of those, the well-known SLEEP model, to consider some underwater additional parameters. So we proposed the U-SLEEP, underwater SLEEP model. And as I said, we like building robots because we're roboticists. And in this case, the robot that we built is for verifying the model. Not yet the final robot. So with this U-SLEEP, we found that the patterns of locomotion have an opposite angle of attack. So you see that the leg is in an opposite position with respect to walking on terrain. And there are longer flight phases, which make sense in water. So you see that the gate is sort of hopping. You see now the images from the robot. What is very nice is that this system behaves like a dynamical model system. You see here how it can keep station, basically with no energy consumption. So we found self-stabilizing gates with this model. so energy consumption is reduced very, very much compared to current underwater robots. So now we have a model. Can we do the last step and design a robot that contains the model, contains the principle, and it can be designed for some purposes. So we don't need to stick on the shape or appearance. And this one is the robot that we designed for a purpose, which is taking samples of sediments to look for plastics. And this is how it works underwater. As I said, the gates are self-stabilizing. There is basically no control. This is just a demonstration of how we can skip any coordination of legs, just having them moving, and obstacles can be negotiated just by the mechanics of the legs. The trick is that legs are compliant, because the motors inside the joints are, they have springs, so they are compliant joints. So we propose one equation for trying to model embodied intelligence for the purpose of designing robots that have it. This is a very general equation where on the left hand side we have a differential operator for the soft body, depending on the Lagrangian or Eulerian view. It changes a little bit, but conceptually it is the same. Then we have one term, which is a nonlinear term describing the soft body mechanics, and two terms here, which are the important parts because they are for the internal and external interaction of the soft body with the environment. All these in the domain of the soft body. So what is interesting is that this is a very general question. Depending on the approach that you want to take, the terms will change. For example, for internal interaction, you see in the table it's quite small, but how the different terms, the N terms change depending if you want to use the continuum mechanics approach or the lumped parameters approach. For external interaction as well, what is important here is just the CX terms. And depending if we are in a fluid or in a solid interaction, you see how the terms change. Just a note about the control. As I said, embodied intelligence is aimed at simplifying control, but you find quite a big literature on how to control soft robots. In robotics, generally, we need this transformation from joint space to task space for controlling the movements of our robot. In soft robotics, this is no more completely true. I mean, we still need these transformations, but they are a little bit more complex because we don't have joints anymore with motors on the joints. So it's a bit more complex. In our simple prototype, for example, with cables that deform the body, what we have is that when we pull a cable, it's one motor pulling, so okay, we can control the motion of the motor, but then the deformation is along the whole arm, and then the tip position, the task space changes. So at least we have more transformation, but still, if we have models for those transformations, we can use the well-known methods. And you find quite a nice literature about the use of model-based methods for the control of soft robots. So they have some limitations, especially in computational terms. So that's why we can take here a brain-inspired control instead. I mentioned yesterday, we discussed this a little bit. I have a background in neurorobotics, so I was already using neural networks to control robots, humanoid robots, and I found that that's quite helpful in soft robotics. You may choose any, let's say, learning approach. And I just show you an example of a comparison that we did years ago with one of our prototypes. So still a very simple robot. in silicon arm with cables. We have the model as I explained, so we know when we pull the cables, we know the deformation of the arm. So we could build just Jacobian-based controller for that. But we also built a very simple neural network doing the same job. So given a position x of the tip in space, we wanted to know the tension T to give to our cables to obtain that position. And we compared the two. Of course, the Jacobian method is more accurate, but then we simulated a little mismatch between the model and the robot itself. Here we simulated that the cables are not perfectly in the center, but they are displaced of 0.5 millimeter, which is very possible with soft robots. So models are often inaccurate because the robots are often accurate. So a soft robot is not as precisely fabricated as traditional robots. And you see in the plot the error, the controllers, in relation to this inaccuracy of the model. So as expected, the Jacobian method has an error that grows with the inaccuracy. The neural network starts with a higher inaccuracy, but this is just the same for any robot, any inaccuracy in the model, because the neural network is trained on the robot itself. So what is interesting in soft robotics, I think, is that we obtain abilities that were not possible before. We can dream of a variety of robots with amazing abilities to be resilient, to self-heal, to grow by adding material, really something that was not thinkable before. And then we can think of many more applications. We have seen something about the applications underwater, especially on the seabed, which is widely unexplored. Applications in the biomedical field, from surgery, endoscopy, up to assistance and also artificial organs. I'm now focused a little bit on assistive soft robots, and they are intended to collaborate with caregivers. So I think there is a very strong relation here with the concept of the cybernetic avatars that you have in your project. Let me go a little faster and give you just an example of a robot that is intended to help elderly people to have a shower. So you see that the robot is soft, but as I explained, what is nice in soft robotics is not just being soft, but having a stiffness that can be changed. And actually, this robot is designed with antagonistic actuators. So there are both pneumatic actuators and cables. So they contrast each other, and we can increase the stiffness to a good level. And this controller can follow a trajectory with a desired value of force. And we are also investigating other, let's say, more fancy way of stiffening our robot arms. In this case, we are using a sort of jamming principle. And I don't know if you're familiar, but with this strange geometry, these particles are enclosed inside a membrane here. You don't see the, anyway. So when the air is removed from the membrane, the structure becomes very stiff. So you see the soft arm here. At some point, the air is removed before the glass is put and the end effector, so that the payload of the overall arm is increased. Let me go towards the conclusions. So I think that soft robotics open up to a more sustainable vision for robots, sustainable from the energetic environmental point of view, from the technical point of view, meaning more usable, but also, of course, as we have been discussing these days, on the else, so the economic, legal, social, and ethical point of view. On the energy environmental side, we don't want to contribute to the growing e-waste. We are at our big market for robots and avatars, hopefully. So we don't want to have these mountains of old robots somewhere in the world. I worked with underwater robots, so of course I don't want to test my robots in the water, in the ocean, if they may be pollutants for the ocean. So I'm studying materials that are compatible with the marine environment and hopefully degradable at some point. And for the socioeconomic impact of robotics, we have seen in these days, my time is over, but I'm also over. I think the right question is what we want human beings to be in the future, and then we should adapt technology to that. Okay, so these are my conclusions. It's basically a summary, so I don't go through it, but I thank you for your attention. I also thank my funding agencies. Thank you.